All right, so we get to talk about boilers today. I know when you all signed up for horticulture and greenhouse technicians, you had visions of getting your hands in soil and taking cuttings and planting, and we got to do that. You will do more of that, I'm pretty confident. But you can't avoid the boiler side of greenhouses. Talk to any greenhouse operator, any grower, and there is boiler interaction. So my job is to give you an overview of how they work, which we've kind of done. We've done an introduction. And today, a little more specifically about how hot water heating systems work and some of their components, and then some strategies. I've got about 7 scenarios at the end of the lesson that we'll work through. So let's get started. So this shouldn't be too unfamiliar. This is actually very similar to the college boiler setup for our greenhouses. There's two. There's almost always at least two, because if one breaks, you at least have some heat, right? Maybe not quite enough, but enough to keep it from freezing to give you time to fix the other boiler. Um, Here's a bed burner style, the ones I don't like that are inefficient. You can see that, the flame happens down here. These are the burners, and it goes straight up and out the chimney. And it's a massive chimney for a thing like that. There's a lot of heat escaping. They're just not very efficient. These are two condensing boilers side by side in a greenhouse. These are boilers supplied by Westbrook. These are a couple of high mass boilers in an ornamental greenhouse. Here's 3 boilers. What's interesting here, you may not see from the picture, there's 2 gas boilers and 1 oil burner, and that's a backup. So should there be a problem, they'll switch. Some communities actually have difficulty maintaining enough gas pressure when it gets really cold, and they may have to resort to a different form of heat. So in this case, oil. Here is a really interesting. This is also a greenhouse, but remember I talked about modular boilers. Look how many there are here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 boilers, right? And those are modular in the sense that if something breaks on it, if it bursts a pipe, all you're going to do is unbolt it, remove the entire unit, and replace it with a new one. And you can bypass it with valves, so the water just goes around it and continues on around the loop. So this is how apartment buildings are done. They're even smart enough to know that as they cycle, so let's say it's not a very cold day and you only need the heat of one boiler, so this one starts and the rest of them don't do anything. Now, if you carried on year after year after year, this boiler here is going to get a lot more use than the other ones. So the controls that they have for these boilers actually rotate which boiler is the start boiler, and it goes around the loop in perpetuity. So each boiler gets the same amount of hours of use as the months and weeks and months go by. Last term, we discussed a little bit about this in terms of heat delivery, right? So under the crop, which could be under the bench or beside roots or under roots. We talked about under the gutter for snow removal. And we talked about, producing warm air for preventing disease. We're going to get a little bit more into that. Maybe not that last one so much, but again, just some quick reminders. These are your rails that a lot of the carts that you work on in a vegetable greenhouse are. They're also hot water. There's some hot water pipes underneath the veggies in these rubber hoses. Then there's perimeter heat in these pipes to make sure it's not cold near the outside wall. And then there's should be, I don't see under gutter, but there should be. This may be a more temperate climate where there's not a lot of snow. I'm guessing that's the case. Anyways, then some under the gutter right here, heat goes up, melting snow, and then there's pipes over top the range where the plants are growing. This greenhouse is a strategy of putting flats right on the ground. So they only have overhead pipes. Now they would have to run these at a high temperature to radiate heat, and they'd have good airflow to move this warm air down and around to keep that crop growing. But often in a scenario like this, it's really cold on the ground. and the crop takes a little longer to grow. They do this because there's less stuff in the way for moving flats around. So typically bedding plant producers, and they don't need a lot of heat because they start in March, and very quickly there's not much heat need. So it's, unless it's a really long bedding plant crop, then they might start putting them in early February, which happens, but usually that's a smaller zone, and the rest of the greenhouse, as it expands out, you don't need all the other heating pipes. We also mentioned hot air blowing down these tubes, which then let it out the sides for uniform distribution. So I think that, and these ones under the flats, you can actually lay your flats right on top of these pipes, and they get nice and warm roots. It's good for propagating. I think we spend time on those things. This is showing you boilers again. Remember, there's the flame, and then 1, 2, 3 passes and out. That's your high mass boiler. So enough of the review. Let's look at a typical heating system design. So I have a boiler sitting here, and it's producing hot, water's coming into it, it's heating it, and hot water's exiting it. Okay, so that's its main purpose. Pretty straightforward. The hot water in a boiler typically goes into what we call a header loop. And this loop just goes around and around and around and around, just keeps going around. And then there's several takeoff points from the header loop, right? We call these zones, where hot water is removed from the loop and added to other loops. So each one of these loops that you see here would be a separate zone in the greenhouse. So let's say this greenhouse has 3 zones. They're separated by halls, walkways, walls, whatever. Each greenhouse zone has its own loop of water that is going around and around, around and around, around and around. And as the warmth in the water radiates out, the water gets cooler, right? And as it gets cooler, the computer says, hey, we need a little more heat in our heating pipes, or our zone's not going to be the right temperature. And so back at the boiler room, this zone connects through what's called a mixing valve, which takes some of the hot water and introduces it to that loop, and takes some of the cold water and puts it into the header loop, and it travels down to the boiler and then gets heated again. So let's look at this a little closer. These are the terms we're going to look at. Header loops. We looked at temperatures for those header loops. We'll look at what we call return temperatures, system pressures. We'll look at some other boiler operational things like corrosion, cleaning, and tuning. But at the end of the day, these top 3 here are the most important for a grower day-to-day operation. So there's our header loop. Let's look at the first thing. It's called the temperature set point. So as a grower, when you're looking at your computer, there are many, many set points. I mean, lots. But from the heating system perspective, you have your header loop is 1. So that's the temperature that's going to be inside this loop, right? That temperature. And these X's, by the way, are pumps that circulate the water. So they're always running. Not always, but they're almost always running. So your loop temperature gives you how much energy is stored in your loop. So let's say it's a winter's night, it's blowing and snowy. You're going to want to have your header loop temperature at near its top temperature to make sure that there's enough energy in the boilers and in that loop to supply at a moment's notice into a zone should it need it. So you might run the header loop at 80 degrees Celsius or something like that, or 85 degrees Celsius, maybe even higher. You're not necessarily going to run your zone pipes at that temperature because that produces a lot of heat that might cook your crop. And maybe your set point in zone 1 is 10 degrees Celsius or 15 degrees Celsius, right? If your zone temperature is dropping, your computer system is going to open up the mixing valve, and it's going to introduce some fresh hot water into that loop and pull off some cold water to go back to the boiler. And then boom, that bumps your temperature up closer to your set point. So now it's on the rise again. until, of course, the energy radiates off again and it has to go back and pull some more heat off the header loop. So hopefully that kind of describes to you how the process works. Obviously, when we're back on campus, I'm going to walk you through this in one of our veggie labs. We'll walk through the boiler system and I'll show you in person, but it's actually a good idea that you understand this before we go there and look at it. So header loop, remember I said you adjust the temperature according to the outside? That's what this graph is showing here. This is what we call a reset temp. So you have higher loop temperatures as outdoors get colder, right? And that way there's enough energy stored that you're not running into problems with your boiler not being able to keep up. So cooler loop temperature as outdoor warm. So spring and fall, you don't need to run your loop temperature nearly as high. So this graph here is sort of a rough idea. You know, at 0, you're running around 70 degrees Celsius. As you go down to -10, -15, we're pushing 80, 90 degrees Celsius in our header loop. And of course, in the spring, when we start heading towards warmer temperatures, we lower the temperature of the header loop. Ideally, we want to try to match the load, right? So let's say, for example, if you ran this at a low temperature and it was -10, there's not enough thermal energy to supply this. The greenhouse will start getting cold, and you're going to have to run your boiler non-stop and hope it catches up. But the flip side is, let's say you have this at 90 degrees Celsius, right? And it's spring, it's +10. There's hardly any heat being lost in the greenhouse. So this loop here is constantly radiating heat and circulating for no reason. And then your zone calls finally for a little bit of heat. Some tiny bit comes out. The boiler might click for a couple of minutes and then go boom, switch right off again. And we don't want the boilers to switch on and off frequently. We want it set up so that the boilers go for a few, like maybe 30 minutes and then shut off. If they go shorter than 10 minutes, we're looking at what's called short cycling, and you end up wasting a lot of energy in that process. I'll talk a bit more about that later. The other thing that boilers have the option of is they can have low fire and high fire. Some of them are completely variable from 0 to 100, but as a rule, generally they often have a low fire and a high fire. And for this, what you can do is in the spring season, when your temperatures are milder, you would run the boiler on low fire, and it does the same thing. It produces less heat, which means the boiler runs for a longer time, and we avoid short cycling. Heck, I'll just explain it now. Essentially, short cycling, the reason it's bad is boilers have to go through several minute, what we call a purge before they ignite. And the blower turns on and it blows cold air to the boiler for anywhere from 30 seconds if it's a very small boiler to 5 minutes if it's a very big boiler. And then once it's purged the boiler, then it releases gas and ignites the pilot, and then it starts the large burner, which then the pilot lights the large burner. And so by the time the boiler's actually up and running, a few minutes have passed and you've gone through a lot of air and blown heat out of the boiler up the chimney. Not only that, it's harder on the boiler. So if you just sort of have the boiler turn on and work hard for an hour or 2 or 3 and then shut off for an hour or 2 or 3, it's a lot easier on the equipment. So short cycling is never a good thing. It cuts into efficiency and wears out your equipment. This is just that temperature reset graph zoomed in so you can see a little bit better. So here's the 0 degrees Celsius mark. So spring, fall, and winter in this direction. So oftentimes the header loop temperature has an automatic adjustment in the computer program. Depending on outside temperature, it will shift it automatically up or down accordingly. So you can look at that in your computer settings. And if your heating system is chronically falling behind, it may be that your reset is not being aggressive enough and not bumping temperatures in the loop higher quickly enough to keep up with demand. One of the other things about header loops, is that we need to be really careful that we don't just, say, okay, here's our header loop is spinning with hot water going around and around, right? And here's our zone. Let's say it's a cold zone. We're growing perennials and it's at 10 degrees Celsius, right? And we let the water get nice and cool in there. And they say, hey, we need heat in zone 1. Let's say this is zone 1, zone 2, zone 3. If this becomes cold, if this section becomes really cold, and then you open a mixing valve and you dump too much cold water into this, that cold water hits the header loop, travels into the back of the boiler, and you end up with cold water hitting a very hot boiler. And I encourage you to watch this video. This is a video showing how much metal expands and contracts based on temperature changes. Shocking a boiler, it's called boiler shock. Shocking a boiler does a tremendous amount of damage. Boilers typically can last like 50 years of service. They're normally very long lasting. And if you have boiler shock, the expansion and contraction wears out the tubes inside and they start to leak. And this shock will damage the boiler in time. So you can shorten the life of a boiler down to, just 5 years if it's really bad. So be very mindful that you're not dipping beyond. Normally the rule of thumb is a 10 degrees Celsius band. So that means that if let's say you're sitting at 85 degrees in your header loop, it shouldn't go below 75 and it shouldn't go above 95. So it's a fairly broad band, but there are times when you see the boiler creeping awfully close to below 75, and that's not good for your boiler. If it's happening over a short time, if you're changing your header temperature and it changes over a few hours, that's not a problem. But you can have a really cold zone dump really cold water into a boiler, and in a matter of 30 seconds, the entire boiler shrinks by 1/4 of an inch. That means everything in it goes under tremendous stress, causing mechanical cracks and whatnot. So typically mixing valves, that's these things, they're not on off. It's not like all of a sudden 100% of the water flows in and out into the loop. It's not like that at all. It's actually a blending. So it takes some of the hot water and mixes it with some of the return water from the zone. So it's blending all the time. And in that sense, that's really the beauty of hot water heat, because it gives you such smooth control over the zone's temperature, such that if your set point is 18 degrees Celsius, with hot water heat, typically the zone fluctuates very little. It'll sort of just modulate slightly, but be right on top. Whereas, if you have a hot water heat, a hot air, like a hanging furnace, that temperature will rise when the furnace is on, and then cool till the thermostat calls for heat, and then rise, and then cool, and rise, and cool. And you end up with uneven climate. And you're more likely to see disease. You're also going to have slower crop cycles in that context. The closer you keep things consistent, the better. So when we're moving mixing valves, there's what we call a limit. And so Matt will show you in your computer systems class how we can see what limits are on mixing valves. So for example, you can limit a valve to 10% of movement, right? So it won't open or close more than 10% every, say, 5 minutes, say 5 or 10 minutes. Depends on your greenhouse and all those other sorts of things. But so that limits how much the valve moves open and then open more, or closing and closing. You give up a little bit of maybe climate evenness, but you limit how much gets dumped on your boiler, causing damage. So as with everything, it's a compromise. Now, if you had a binary hot water system where you had a boiler and a tank, and you had all the water going to a zone and then coming back, you would have boiler shock every day of the week, and your system wouldn't last very long. Plus, you wouldn't have very good control over the climate, because you would end up having really hot and then really and then when it shuts off, nothing. So that's in the case where there's no mixing valves. This is in a boiler room. These are showing you what mixing valves look like. You can see that there are pipes coming in, pipes coming in, pipes coming in, pipes coming in. So one side, usually the bottom here, is your header loop, right? So that's your header loop. And the top is your zone loop. So this is your zone loop. And this particular greenhouse has what looks like 1, 2, 3, 4. 4 mixing valve, 4 zones. Yeah, I could actually read my slide, and then I would see that I already wrote that. Anyway, so 4 zones, 4 mixing valves. Each zone has its own pump, right? That's going to move the water to the zone and bring it back. This is just showing how a mixing valve works. This is when it's closed. This valve is closed, so all the water just comes in and goes out on one side, comes in and goes out on the other side. As that valve can rotate completely to 100% open, then all the water goes in this direction and all the water goes in this direction. Now, if you have the valve at 50%, then it blends and some goes this way and some goes the other. So that's how the mixing valve works, essentially. So pipe temperatures, when we've talked about pipes and stuff like that, whether it's under bench or under crop, there's different temperature set points. Obviously, right under the crop, you can't have it really, really hot or you're going to cook the roots. Under the bench, you can run higher temperatures because it's not direct contact with the roots. Remember last term we talked about activation temperature, right? So particularly in tomatoes, that's shown to improve yields by about 20%. That's pretty significant. It does cost more, a little bit more in gas, but that more is then offset by the increased yield. So that's where we talked about waking up the crop. Activation temperature was waking the crop up in the morning, getting it going, starting transpiration so we could get the crop going and ready for its first irrigation. Perimeter heat, we mentioned last term about how the pipes that go around the outside of the greenhouse will help prevent cold spots. So if you're, if this is a side wall, you're in your greenhouse and here's your crops, and outside here is the north side. This is a cold wall. It's always getting cold wind and no sunlight. So we have extra heating pipes along the perimeter to make sure that that zone doesn't get too cold. That's a terrible drawing. I hope you can understand what I was trying to say. And we mentioned under gutter heat for snow removal, that sort of thing. And it's important, again, to reiterate that a lot of this is controlled by the computer system, which, of course, you have control over as a grower. Another really important part about a boiler system is the fact that it operates under a certain amount of pressure. So reminding you about a couple of traits of water, right? Straightforward. Water boils at 100 degrees Celsius. I think we all know that. But if you put pressure on the water, like in a pressure cooker, the water takes longer to boil, which means one of the reasons pressure cookers are so fast, that you can go higher than 100 degrees Celsius inside a pressure cooker. And of course, hotter temperatures means quicker cooking, right? So what we do is we apply pressure to the entire system, and that raises the boiling point. And typically, we don't usually run at 100 degrees Celsius, but for safety's sake, having some pressure in the system reduces the risk of steam forming. If steam were to form, we could have an explosion, which would be bad news. As I mentioned in the last class, right? So system pressure keeps air pockets from forming, right? That can create an airlock. I'll talk a little bit about more of that coming up. Which, when you get an airlock, that prevents water from flowing through your pipes, and that's no good. So then all of a sudden you have a cold zone. You can't figure what's going on. The water's not flowing. You don't hear any gurgling sounds, or maybe you hear gurgling elsewhere, which means there's air. So you got to get that air out of the system. So some pressure in the system keeps the air pockets compressed so that they're small, and the water will continue to flow. One of the other reasons why we have pressure in a heating system is to prevent what we call pump cavitation. I've got a couple of slides coming up to explain these a bit more. So airlock, this is an example of a reservoir that has a pipe that's draining from the reservoir. And if air gets in the pipe, what actually happens is the liquid won't flow because the air pressure doesn't push the water over the rest of the system or around. And so air in the system will actually stop the hot water from flowing and you get cold. So we put pressure on the system because then those air bubbles are smaller and may only occupy a small area, which then allows the water to flow anyways. That's one reason for why we pressurize. So there's two now. We know we pressurize because if we have to have a high temperature, we don't have to worry about it boiling. We pressurize because it compresses air pockets to make sure we don't get airlocks. And lastly, we pressurize so we don't get cavitation. Cavitation is when you have an impeller pressing or pushing water. If the water is, if there's a fair amount of force on pushing the water, it actually pulls a vacuum behind the propeller. And that's what you're seeing in this photograph here. This is bubbles forming in the water behind the propeller as it spins. I don't know if you've ever been in a motorboat where someone accelerates too quickly and the boat just revs and nothing happens. That's because the propeller is cavitating and it's formed a vacuum, and the propeller is actually spinning in a pocket of air in the water. This is a really good video to watch. I think it will explain better for you to understand what cavitation is. So I encourage you to watch that video in your PowerPoint version of this. But essentially, if we have pressure in the system, that makes it more difficult for cavitation to happen. So, and where we get cavitation in the heating system, if you recall, there are pumps that move water all over the greenhouse in the different zones. And those impellers can cavitate. And if they cavitate, they don't move the hot water. It won't get to the zone. And on top of that, it starts to wear out the pump. So pressure helps alleviate cavitation. Now, typically, systems maintain a certain amount of pressure via two methods. So one is called an open system. Okay, so an open system. And the other is called a closed system. So an open system has what's called an atmospheric expansion tank. That means that the system is pressurized. The entire heating system is pressurized. And there is a tank similar to this that's connected to the heating system, and that allows water to sort of come and go out of the system or into the system, and it monitors the pressure. The closed system is where you're connected to a pressurized pump system, and it needs a closed expansion tank. So similar to if your house has a pump and a blue expansion tank, there's water and a little air pocket in the top that compresses as you add water. And then when you pull water out, it expands. So this is really hard to explain via PowerPoint. So I will definitely be going over this again with you guys in person at the greenhouse. But I have another slide coming up. Hopefully this will clarify some of what I'm trying to say. But essentially, we know that we pressurize the system. There's two main ways to do it, and they both have their advantages and disadvantages. But what I mostly want you to remember is the fact that the system is pressurized, and that this expansion tank kind of shows you where the most critical water level is in the whole heating system. Because if there's a leak in the system, this tank shows it first. There's often glass or plastic tubes that show how high the water is in the tank or how low. So I'll explain that again in the next slide. So, all right, coming up. But so water expands as you heat it. Water is interesting. It's most dense at 4 degrees Celsius. But as much as 4% increase in volume at 100 degrees Celsius. So looking at a typical heating system, a 1 acre greenhouse, that means that the water in the entire heating system will expand or contract by 200 liters. That's quite a bit. That's like a full bathtub right to the top. So that will either appear or disappear based on just the system heating or cooling. And when you have a closed heating system that's all in pipes that don't flex, how do you accommodate that expansion? Because we're talking a huge amount of water that you have to accommodate. So in the closed heating system, as the heating system expands as it gets hotter and the water takes a larger space, that is accommodated by the expansion tank. And in the open expansion tank, it's the same, except that that tank is open to atmosphere. It's not sealed. So typically the expansion tank here, you can see there's a tube on the side, and you can't quite see, but the water level's right about here. So that's probably normally a safe level. And this boiler system, this is the expansion tank. The sight glass is on the side here. It's pretty standard stuff for boiler rooms, and probably one of the first things you're going to check whenever there's a boiler fault, because more often than not, there's a small leak somewhere in the greenhouse. Maybe an employee stepped on a pipe, made a crack, and it's been dripping. And after a couple of weeks, the system's lost enough water that now the expansion tank is below its low level. There are usually there's usually a low-level sensor on the tank that trips an alarm for your computer system. And then that usually happens at 3 a.m. in the morning, not at 3 p.m. So then you have to get up and you got to go to the boiler room and see what's going on. And so you should know where your expansion tank is. It's a closer look. Here's a reset button for the alarm once you've checked it and you've added water and everything's fine again. You definitely want to find the leak if that's the case, right? But it'll be fine till morning. A lot of boilers have what's called a combination gauge. On the top is temperature, and on the bottom is pressure. So this is sitting at 58 psi. That's actually pretty high, if you ask me. Boiler systems are usually around 15-20 psi, pounds per square inch. And if you're metric, kilopascals, so that's what 100 kilopascals, which by the way is similar to atmospheric, right? Because we're at what, 101 kilopascals from sea level. So, you know, oh yeah, sorry, this is the alarm here. There's the pressure. The main gauge, I'm so silly. The main gauge is sitting at 20 psi. That's what I would expect. So it's about 50 kilopascals above atmospheric pressure. Not a huge amount of pressure, but it's enough to make sure there's no cavitation and the water's flowing everywhere in the greenhouse. Okay, let's move on. Anti-corrosion, I'll just mention this briefly. I don't think it's really that important as a grower, but it's important to be mindful of it. Boilers and everything are made of steel, mostly. There's sometimes some copper, some stainless steel, but it's generally steel. And steel rusts, especially when there's oxygen present. So we have to make sure we're not, if you have leaks, that we fix them, because if you're constantly adding fresh water, water has some oxygen in it. So when you introduce fresh water, you're introducing fresh oxygen, and that just accelerates the corrosion of the entire system. Boiler systems are treated usually on an annual, sometimes semi-annual basis with chemicals to reduce corrosion. Similar to what happens to your car, right? So there's molybdate is added, which is, you know, a form of molybdenum, which is a nutrient, and nitrate, which is a nutrient. So these are not like majorly toxic things, but these elements, these chemicals will scavenge oxygen and prevent corrosion. Typically this is done by a contractor, and they come in and check it and send you a bill for checking, or bill you for another barrel of molybdate to add to the system because the levels are low. Cleaning boilers once a year when the greenhouse is empty. In the summer, you open it up, all these tubes, you get a brush, punch them down the tubes to clean it. That improves your heat exchange efficiency tremendously. Okay, so we talked about condensation at an earlier lesson and last term a little bit, but condensation in boilers happens when your temperatures are too cold. So remember I said there's a reset temperature for the boiler. You can have the boiler hotter when it's really cold out and warmer when it's not so cold out. There is a bit of a limit, and that is we need to make sure that our boiler is not running so cold that our temperatures are cold enough that we get to the dew point and we get condensation forming. When you burn natural gas, there's a trace amount of nitric acid in the condensate. So if you have a boiler that is, crazy efficient and not designed for it, so you're running your boiler at a cool temperature, and just like you're in a car at the intersection, there's steam coming out the back of the car and water dripping from the exhaust. The same thing would happen to your boiler. You get lots of steam, but the steam condenses in the chimney. It doesn't make it out the chimney. And so that nitric acid in the condensate travels down the chimney and erodes the metal and eventually rots the chimney right off, as you can see in this picture here. That's the nitric acid eating it away. So typically what we want to avoid is we want to avoid our chimney stack temperature going below 58 degrees Celsius. That's what I'm circling here. So we need to make sure our flue gases don't get too cold. And if they do, we have to have a stainless steel chimney that will trap the condensate. So remember how I talked in last class about economizers that collect the heat out of the exhaust gas from the boiler to improve the efficiency. Those are made from stainless steel. They're designed to collect that condensate and channel it into the ground. Some greenhouses even collect the condensate and put it into their nutrient tank as nitric acid, which is smart. Sometimes it's kind of dirty. I don't know if they filter it, but a lot of farms just put it into what's called a French pit of limestone gravel, which then is neutralizing the acid. So we have to be careful that our flame size, if you have a high-low burner, when you're on the low fire, make sure that you're not forming condensate in the chimney. You'll see water dripping from the boiler if that's the case, because it'll drip. Condensation will drip down the chimney into the boiler, and it'll drip off the back of the boiler, and you'll see water in the ground. So, for example, it might look like your boiler has a leak, but in fact it's condensation, which is really bad news because it's going to eat through your boiler in no time. So in the spring and fall is when this is more often an issue. So be careful about that. This is just showing you once again how when the exhaust gases, when they go below a certain temperature, in this case 138 degrees Fahrenheit, the condensation forms quickly and you get heat loss into the chimney. So that's where your condensing boilers are efficient, but you get all that condensation forming from here on down. I'll briefly mention fuel efficiency. Last week I talked about BTUs and efficiency ratings. So boilers are usually tuned by a professional that have devices that measure oxygen and carbon monoxide in the chimney, and they'll tune the boiler so that it has the right amount of air and fuel so that it's efficient. I'm not going to ask you to memorize this, not at all, but I want you to know that, a properly tuned boiler will save you lots of money. So it's worthwhile having it analyzed every couple of years, or at least once a year, I would say. This is what a natural gas burner flame looks like when it's burning properly. It's got a good spread on the color, a bit of an orangey tinge, mostly blue. If you see lots of lazy orange flames, it's running very rich and sooty, and you're wasting your money. You're not getting a lot of heat out of it. I say this only because if you end up at an older, smaller farm, this stuff is going to become invaluable. If you end up at a fancy high-tech place, they're going to have professionals on staff. They're going to take care of this. I have to prepare you for sort of all scenarios. But definitely growers at smaller farms end up dabbling in all sorts of things around the greenhouse that they probably never thought they would. One other comment about pumps. These are all the circ pumps. There's your header circ pump. There's your zone circ pumps, circulation pumps. There are things like dust, water dripping on them gets into them and rusts them or shorts out the electrical. Bearings wear out, seals wear out. These are very common wear points in a greenhouse where you run into alarms. And if you want to do preventative maintenance, you go to the boiler room and you see that there's water pouring out from these slots. That's where the shaft goes into the pump. Your seal is gone. Water will be pouring on here. There'll be corrosion all over the place, crystallized molybdate from the anti-corrosion chemicals. It'll just look ugly. And proper maintenance when the summer comes is to pull this motor off and service the seal. You don't have to do that. There's companies that do that, but you're going to have to point it out and insist that it gets done, because if you don't do it in the summer, it's going to fail you in the winter. I want to talk lastly about buffer tanks. Not quite. Yeah. So on the right here, we have a greenhouse, and you see there's a very large tank. These tanks are full of hot water, and they have become almost an industry standard in greenhouses that are above a few acres. We had one at our greenhouse, and it saved us a lot of money. What they effectively do is they store heat. All right, so you'll see there's a pipe coming from the top, and there's a pipe at the bottom. They both go to the boiler room. So a buffer tank allows you to decouple heat production from CO2 production. So that means that, for example, and I mentioned this last term, when do you need CO2 for plants? At night or during the day? You need it during the day when the sun is shining. Now, when the sun is shining, you don't always need heat. When do you need a lot of heat? You need a lot of heat at night when the sun's not shining. So we get our CO2 from the boiler, but we get our heat from the boiler. So what we can do is we can reverse the flow. And during the day, we run the boiler and produce CO2, which we pump into the greenhouse to fertilize the crop. And the heat goes into the tank. And then at night, we reverse it. So normally we're putting here, and it's coming out here. So the hot water comes out at night, heats the greenhouse, and eventually in the morning the tank is cooler. Maybe not completely cold, but it's cooler. And then the process repeats itself. So heat storage tanks, there's a lot of writing here, sorry. Heat storage tanks allow us to decouple heat production from CO2 production. They also provide emergency backup. So if your boiler quits, you usually have anywhere from 8 to, I'm going to say, 16 hours of heat sitting in that tank, which buys you enough time to fix your boiler and get up and running again. It also allows a smaller boiler to provide a larger burst of heat. So let's say, for example, if your greenhouse needs, let's say, X amount of heat for the duration of the day, and you have a small boiler, instead of having that boiler cycle on and off and on and off to maintain the greenhouse temperature, what if you just made a smaller boiler that turned on all day and never shut off? And anytime the heat wasn't needed by the greenhouse, it's diverted to the tank. That way, when there's higher demand parts of the day, which typically are the morning and the evening, the tank makes up the difference, and the boiler can just chug along at its normal speed, and the tank gives that big burst of heat in the morning and then settles off, and the boiler slowly recovers during the day, producing nice CO2. And then towards the evening, when the sun goes down and the greenhouse is getting cold and you're trying to get that last bit of growth out, the rest of the heat pours out of the buffer tank to finish off the day. And then through the night, the process recovers again. So smaller boiler means more efficient. It's working hard and all the time. That's a more efficient boiler. With is less cycling, right? Fewer on-off cycles. So these are kind of related. So buffer tanks are very important. Normally the greenhouse computer will report various temperatures on the tank. They often have sensors that are, maybe top, mid, and lower. Often more sensor points than that, but that's okay. And the boiler, obviously hot water rises, so you pull off the top and you feed in the bottom. There are some boiler or buffer tanks that are more sophisticated and have multiple takeoff heights. So you can leave the higher energy water behind and pull just specific temperatures off into your heating system according to the demand. Let's look at some scenarios. I got 7 of them to go through here. So scenario 1, you log into your greenhouse computer in the morning and you can see that the energy curtain has opened, but you notice that the zone temperatures are 5 degrees C below their set point. What should you change to prevent this in the future? Now remember, last term I had this question on a I think it was your final exam, right? So some scenarios, what can you do? You've opened the curtain, you see the curtains opened, and you notice the temperatures are too cold. So you can increase your header loop temperature. I can't write with my right hand. I'm so conflicted here because I'm left-handed, but I mouse with my right hand, which makes it really hard to write. So you can increase your header loop temperature, which produces more energy, so the greenhouse doesn't fall behind, right? You could start your activation temp earlier. You could delay your energy curtain, or you could open it in smaller increments. This is kind of just more of a review question. I just wanted to introduce the concept of the header loop because that didn't necessarily make sense last term because we hadn't talked much about it. So anyways, I'll let you think about some more scenarios or more answers to that. There's many actually. Scenario 2, you hear a gurgling sound in the pipes under the benches and some benches are not getting heat. What could be a possible explanation? So gurgling means what's in the water? Air. And if you're not getting heat, that means you have an air lock, which means there's air in the system or the system doesn't have enough pressure or both. What could be a possible explanation? So there could be a leak, right? You got a leak and water levels are low. Your expansion tank is leaking and your PSI is low, your pressure on your gauge and your boiler is low. So you need to add water and get your pressure up. Scenario 2, you look at your computer graph that summarizes how many times the boiler is turned on in the past 8 hours. It looks like the boiler is firing every 15 minutes and staying on for only 3 minutes. What should you change? So that's bad news. That is absolute horrible short cycling, right? So what do we need to do? We need to make sure the boiler stays on longer. So there might be something going on with your mixing valves that the changes are too minute and the boiler very quickly reacts. But probably the biggest thing to do is to lower your header loop temperature. So this could be like a spring scenario. Let's say you forgot to change your header loop temp and it's still the same settings that were back in February, but now it's April and it's plus 10 outside. So the boiler is going to hit your heating requirements in a matter of minutes and then shut off. That's no good. So you got to lower the loop temperature as much as you can without allowing condensation to happen, right? Scenario 4, your crop looks like it's running behind schedule. What changes can you make to accelerate its growth? This should be straightforward, right? Number one thing that affects crop growth rates is temperature. Increase the temperature. You're running your zones too cold. Sometimes farmers like to save money by turning the temperature down. I know I'm accused of keeping our house too cold because I'm a cheap farmer. And to be fair, my kids are short too, so maybe it's temperature related, but I don't think so. But anyways, saving energy is great, but saving it at the expense of finishing your crop on time for a ship date is a huge business problem. So watch if your crop is not hitting its growth targets on your plot. Remember how you plot your growth of your crop? Say these are acceptable ranges and normally you're here, but let's say you're falling behind. You need to increase your temperature to keep your crop growth within that curve. Scenario 5, you receive an alarm call indicating that you have a problem with your boiler. What should you do? This is meant to be a generic question. It's like, I don't know. Well, I'll tell you this. Typically, as junior growers, you're the first person on the call. And if you just flip your phone off and go back to sleep, you may have made a multi-million-dollar mistake. So what do? You act. I know this seems crazy to say, to have to point this out, but it is critical that you act. What do? You're going to log into your computer. You can do that from home often and see what the problem is. It doesn't, I'm going to guarantee you, you should not just reset something on your computer and go back to bed. You can silent the alarm and go to, but then you have to go to the farm and take a look with your own eyes and see what exactly is going on. If you don't know what's going on, the next thing you're going to do is you're going to call the next person in charge and tell them what's going on, even if it's the middle of the night. They're not going to care. You woke them up, doesn't matter. They have multi-million-dollar crop in that greenhouse. They're not going to complain if you're up in the middle of the night trying to take care of it. That's your job. Scenario 6. It looks like water is dripping from your boiler. You confirm that there are no leaks. What needs to be changed? What do we have here? We have condensation. Let's write this all out. I'm getting a little bit better at writing with my right hand. This is like, what's that? Etch-a-Sketch? It's just as hard. Condensation. You're running your boiler too cold and your return temperatures are too cold and you're getting condensation in the chimney and it's dripping out your boiler. You definitely need to increase your header loop temp, right? And you need to limit your mixing valves because they're dumping cold water into the boiler loop, too much cold water. Now, here's the situation. If you limit your mixing valves without increasing your header loop, your greenhouse will start to get cold because limiting the mixing valves means you're limiting how much hot water can go into the zones, which means they don't have as much heat. So you'll watch your temperature and your computer will just start to get colder and colder and colder. So you can't do that. You have to increase the header loop temperature and at the same time look at your valve limiting, at least till the greenhouse recovers. Often computers have what we call a temporary limit. So it will, for 30 minutes, limit the valves to 10%, and then it defaults back to the normal one. They do this so that you don't leave it at 10 by accident. Kind of smart. Scenario 7. You get a buffer temp alarm, right? That's the top of the tank, let's say, is below your set point. What must you do? What must you do? So your buffer tank alarm goes off. How do you fix that? Well, that's a tricky one. If your buffer tank is falling behind, then you're not putting enough heat into the system. So once again, increase your header loop temp, right? Check that that is suitable. Make sure that the greenhouse is not pulling from the tank when it shouldn't be. So look at your limit settings for the mixing valves on the buffer tank. What can't you do? Oh, that's an interesting. What can't you do? Any ideas? But one thing you can't do is help the system react to very quickly because these buffer tanks are so big. This problem will take a few hours to rectify. So you can't fix it quickly. How could this happen? You may have a boiler down, so one boiler is not operating, right? That means that you don't have as much heat going into the tank, so you didn't store enough heat over the day. Another possibility could be that your energy curtains are not closed and your greenhouse is losing more heat than it normally would. So check your energy curtains. They don't always trip an alarm. What should you change to prevent this from happening again? Well, it really depends on what caused it. But what you might want to do is set an alarm a little closer to, a little further from the set point to give you more advanced notice when things are going wrong. Waiting till the top of the tank is below set point is really late in the game. But again, you can prevent it by, looking at your valves, looking at your header loop temperatures, looking at your energy curtains, looking at your timing for when heat comes and goes. Maybe you might have to ramp the temperatures more slowly instead of going from 16 to 20 degrees Celsius in an hour, you might have to do it in 2 hours. It might mean you're undersized for your boilers. Maybe your boilers need to be tuned. Maybe they're not operating on high fire. Maybe they got switched to low fire. That won't trigger an alarm. So you have to check that. So this is meant to give you a taste. I'm certainly not going to try to turn you into 100% skilled and trained boiler operators, but this is to give you a taste of the kinds of things that you'll run into. So next time we're on campus, I'm going to walk you through the heating system, and I'll show you this all in person. And I know that the expansion tank part will make a lot more sense when we're there. So bear with us. We're still coming back to campus. Good news. All right. Take care.